I must say, having the organizers give their talk on the very first day sounds like a good definition of masochism, but when the other speakers were going over their slides for their talks tomorrow, I was making badges at last. But anyway, let's see. If I fall asleep, someone wake me up. Yes, page down is difficult to find on this keyboard, isn't it?
It's there.
Yes, yes. I'll just explain. So you know Rob Corliss. Yang Wang was a student in Rob's experimental maths course and did most of the calculations for this paper. Joshua was a student of mine some years ago and started the project, although he didn't make any, he only made background contributions to the current paper, but I thought he deserved to be mentioned. So I'm going to define Stirling functions, Stirling numbers first, for those who don't know them. I'll define them for integer arguments. Then I'll talk about various attempts to generalize those definitions to real numbers, ending with Flageolet's definition. Then we have the problem of turning that into a computational recipe. And so we're going to be using the trapezoidal rule. And for those of you who are not numerical analysts, you may remember that the trapezoidal rule is something you're taught in first year calculus. And if you had n panels, you're taught that the integration is accurate to 1 over n squared. But it's less well known that there is a class of integrands where it is exponentially convergent, and we can manipulate Flageolet's definition into this format, and I'll demonstrate that we get exponential convergence.
Is that called self-flagellation?
Who let him in? Then finally, when Flageolet proposed his definition, some people, particularly Knut, were worried about its value when the arguments were 0, because it appeared to conflict with his definition in concrete mathematics. And so in the spirit of this, we got Yang to calculate values of this definition around the 0 arguments, and we'll see what happens there. So that's what goes on. Just to settle notation plus definitions, we're using Knut's notation. So the rising exponential, rising factorial, z times z plus 1 times z plus 2 up to n factors. Stirling introduced his numbers because he was trying to accelerate the convergence of series, and he liked to convert an ordinary power into a rising exponential, and in order to do that, he needed these numbers here, and so they become Stirling numbers of the second kind, even though he introduced them first. And they're written with braces because you think of sets, because these have a combinatorial interpretation as given n objects, the number of partitions into k subsets. So we call these Stirling partition numbers, also called Stirling subset numbers, or as I said, Stirling numbers of the second kind. He also has, if you go the inverse relation, Stirling numbers of the first kind. These are Stirling cycle numbers, but we'll mostly be talking, in fact, entirely talking about the partition numbers. They have a generating function, which is e to the z minus 1 raised to the k. So if I expand that as a series, the coefficients are Stirling numbers, and if I use Knut's notation of extracting the coefficient of the kth power, then that gives me that formula for the Stirling numbers. So that's definitions for integers, and then the question is, in one of Knut's books, I can't remember whether it's Concrete Mathematics or The Art of Computer Programming, he actually sets a challenge to extend the definition to arbitrary arguments. he had a first go at it himself, introduced Stirling numbers for half integers, but oh yes, I've written it here. In concrete mathematics, he says the challenge of finding a good generalization. So so he chose to, this is a recurrence relation which is true for integer powers. He tried to use that as the basis of the extension, but it had some disadvantages to it. Then in '94, these two used this identity and used that to extend at least to n being an argument, an integer, and k being, oh, I've said z, that's k being arbitrary. And they call them semi-real Stirling numbers. Then up the road at Waterloo, Richmond and Molini proposed, so you recognize this as the generating function, and you would recognize this as the contour integral, that if x and y are integers, then this is just another way of extracting the nth coefficient of the series. And they proposed using this as the basis of the extension. Now, once you have x and y as real numbers, you're going to have branch cuts because this is a power here. And so the question is, what do you do with the branch cuts? And they made they kept integrating around the circle, made one assumption, but some of the classical identities fail. So finally, Flageolet and Pottinger suggested that because we've got a branch cut here, this is a plot of the integrand, they suggest a Hankel contour which goes around. And so that is now the proposed definition that we're going to study. So now we switch to what I said before about the exponentially convergent trapezoidal rule. So you're all familiar with this from your duty to teach first year calculus. But so this was reviewed by Trepethen and Biederman. And they reviewed work going back to the 50s. Sorry.
Yeah, but that's actually not the trapezoidal, that's just a block.
Oh, sorry, yeah, that's right. Oh, yes,
The
you're right.
trapezoidal, you have to average.
Yes, sorry, you're right, that's the midpoint rule. That's
analysis
That's the same thing. It's the same result, yes.
Yeah, it still applies.
Same difference. So Trepethen and Biederman collect examples in which the midpoint rule or the trapezoidal rule converges exponentially, and they list three possibilities here, and the last one, Hankel contours, is the one that we are interested in. These were introduced first in the 50s in the context of inverse Laplace transforms. John Butcher in New Zealand, known to some people in the room, suggested it, but didn't follow it up, but other authors have done so. And we're going to be using that. So before we apply the trapezoidal or midpoint rule, Flageolet and Pottinger integrated by parts. They did it because this converges only for a positive real part of z, whereas this converges for all z. But it has another important effect, which is we pick up an e to the z here, which makes the integrand decay exponentially for large negative z, and that helps our convergence enormously. So this is the integral we're actually going to evaluate. So there are many possible choices. All we need for a Hankel contour is that it comes in, goes around anti-clockwise, and then goes off to infinity again. We choose this particular contour. It just happens to be the boundary of lambda w, although that's not really important for this context. And we see that this will go from minus pi to plus pi, and as we approach, you see we get this exponential convergence decay, as I mentioned. So that's really easy to, well, it's just midpoint rule, so it's only a few lines of code to implement it. So just to test it, we've just calculated the integral for something that we know. So Stirling number 5.3 is 25. And we've plotted that against increasing number of panels using MATLAB. And so you see the error decreases. And then once we hit 10 to the minus 15, we get that usual rounding error fuzz, as you can't go any further than the accuracy of the floating point system. If we increase our digits to 50 and change to maple, we can see rather more clearly the shape of the error. And once again, when we get down here, again we get the fuzz of rounding error. So what we'd like to do is explain that error. And if the error really goes like c to the minus the square root of n, then the log of the error plotted against log of the number of panels should be a straight line. So I cranked up maple to 100 digits and left it running for a day. And there it is. And the blue line is a straight line with slope a half. So that verifies that the errors are indeed obeying exponential decay as c to the minus square root of n. So finally, how are we going? What is the value of the Stirling number of 0, 0? So in concrete mathematics, it's defined to be 1, and the reason for that is simply that there are a large number of summation identities, and if you have this definition, then the first term in the sum can be folded in with all the others, and you can start your index from 0. Whereas if you have any other definition, then your identity would have to be one term plus a sum for everything else. However, when the Flageolet's definition was introduced, it looked as though the natural definition according to the integral version would be 0. And so the question was, which should prevail, the concrete mathematics definition or the one implied by the integral? However, if we look at it a bit more carefully, we see that n is 1. So if I've got n objects, then I'm going to partition it into n subintervals. Obviously, there's only one way to do that. And n0 is 0 from the integral. So as n goes to 0, obviously we have a conflict here, and they can't both hold. So what we asked Yang to do was to evaluate numerically x over nn. In other words, approaching the origin point 0, 0 from every possible angle. And he produced this conjecture based on the numerical evidence that as you approach the point 0, 0, you can get any value you like, just depending upon the angle you come in at. So given the fact that this shows that if you take this as your definition of the generalized Stirling number, at the origin there really is no natural definition for the value, at least based on this integral. And so if that's the case, and from the point of view of summation theory, seems to be perfectly reasonable to stay with 1 as the value at 0 to make the series work. I don't know how many of you, when I became a graduate student, I discovered that many of the senior professors had filing cabinets with yellow pieces of paper full of promised projects that they never got finished. I have a bit of paper in my filing cabinet from about 20 years ago saying I shall implement generalized Stirling numbers in Maple, but I think I'll go and have lunch instead.